Hello everyone, my name is Dr. Ranjith Kumar Gatla. I am working as an associate professor in Department of Electrical and Electronic Engineering, Institute of Aeronautical Engineering. Today we are going to discuss the Scr Commutation Techniques. In the last class, we have already discussed what are the different types of commutation techniques, and before that, what is mean by commutation. The commutation is nothing but the process of turning of the thyristor is called as the commutation. And majorly there are two different types of commutation techniques based on the input supply that we are giving to the thyristor. So if you are giving the supply as a AC supply, then in that case usually the natural commutation will apply to turn off the thyristor. And in the second case, when the input supply is DC source, then we use the forced commutation techniques. So there are different types of forced commutation techniques like the class A commutation technique and class B, class C, class D and class E commutation techniques. And class F commutation technique is about the natural commutation technique. These things that we have discussed in the last class, in the previous class. So now, in the previous class we have already discussed what is class A commutation and what is the procedure that we are going to follow to apply the class A commutation to turn off the thyristor. Similarly, class B and class C also we have discussed in the previous class. So in this class, we are going to discuss the class D commutation technique. Here, the class D commutation technique is also called as the impulse commutation. And why it is called as a impulse commutation, that we will get to know. And here, again we are considering the two thyristors. One is thyristor T1 and another named as a thyristor TX, which means the thyristor T1 is the main thyristor. So to turn off the main thyristor T1, so we are using the axillary thyristor TX. So that's why this is also called as a axillary commutation technique. Unlike in the previous case in the type C, the class C commutation technique. Okay, so there that was the axillary commutation. That was also because there we turn on the there also we have considered the two thyristors, and in the two thyristors, so we use the second thyristor to turn off the first thyristor. Similarly, we are using the first thyristor to turn off the second thyristor. But unlike here, the main thyristor is T1. Okay, we are going to turn off the main thyristor T1 by turning on the auxiliary thyristor TX. That is the process that we are going to do here. So that's why this is a auxiliary thyristor. And again here, in addition to the thyristor T1 and TX, we are using three more components, which are the capacitor and the inductor. So as we know, usually the capacitor and the inductor we call as a the commutating elements. And next, in addition to that capacitor and inductor, we are using the diode also, because just to give the forward biased flow. So here, how we are going to apply the commutation technique, or how we are going to apply the class D commutation technique to turn off the thyristor T1 that we are going to do. So here, mainly before going to the process, here mainly we are assuming the two assumptions. The first assumption is the load current is constant, that we are going to consider, and another one is the capacitor C is initially charged by the voltage V. The capacitor C is initially charged by the voltage V. Then in the first case, initially let us consider the thyristor T1 and TA in the off state, so that there is no path for the current flow through the load. Then after that, in that case, when both the thyristors are turned off, okay, so as we considered the assumption, the capacitor is fully charged by the voltage, that is VDC. So that's why here the capacitor terminals are the plus and minus. Okay, then by giving the gate signal T1, by giving the gate signal to the thyristor T1, we are turning on the thyristor T1. Then the load current will flow through plus VDC from here plus VDC to this SCR to the RL load to minus VDC. This is the path that the load current will flow. And again, as we considered, as we assumed, initially the capacitor is fully charged. Okay, so which means the voltage across the capacitor, which is equal to VC, is equal to VDC. Then here the commutating current, actually here the capacitor current is also called, I mean this capacitor now is going to discharge. Okay, then this the same okay, I mean in this case the capacitor will act as a source. Okay, then the capacitor current are also called as a commutating current. Okay, will flow through the path from here to here, from this capacitor positive terminal to thyristor T1 to inductor L through diode to the capacitor negative terminal. This is the commutating current. So then once the capacitor discharges fully, okay, because here now it is discharging. So once the capacitor will get discharged fully, then the terminals of the capacitor will change, and then it will again, what is that, a charge in the reverse direction. Once the capacitor get, I mean because in the first case initially we have considered the capacitor is fully charged, so that's why when the thyristor T1 is turned on, so the load current will flow from the plus VDC to thyristor T1 to load to then the negative terminal of the VDC, and in addition to that there is a current, that is the commutation current or the capacitor current, that will also flow, because here the capacitor is discharging because initially it is fully charged. So we are providing the path to discharge the capacitor C through thyristor T1 to inductor to diode. So that's why it will discharge. So once it is discharged again, because anyway we are supplying the VDC, so that's why again it will charge. Okay, but in this case when it is discharged, the terminals will change, like here minus and plus, then it will charge in the reverse direction, which means the upper plate is the negative and the lower plate is the positive. When the capacitor is fully charged, when the capacitor is fully charged in a reverse direction, then there is no path to discharge this capacitor, because in this how it is charged, because this is minus and this is plus. So here the reverse, because in this way it will not flow, and in this way also it will not flow, because here the diode will not allow the reverse biased voltage. So that's why here there is no path to discharge the capacitor. Then to discharge the capacitor, here what we are going to do is, which means to turn off the thyristor T1, here we are going to turn on the auxiliary thyristor Tx by giving the gate signal. So here if we turn on the thyristor Tx, okay, then here already the capacitor terminals are changed, which means the capacitor is fully charged with a voltage Vc is equal to minus Vdc. Then here we are providing the path to discharge this capacitor. So then the capacitor will discharge in this way through Tx, which means the positive terminal of the capacitor to Tx to T1 to the capacitor C, which means the reverse biased voltage applied across the thyristor T1, because here you can see this is plus and minus, because the cathode is connected to the positive terminal of the capacitor and the anode is connected to the negative terminal of the capacitor. So that, which means the reverse biased voltage applied across the thyristor T1, then the thyristor T1 will get turned off. The thyristor T1 will get turned off. Right. So in this case, then the thyristor T1 is off like this, okay, and the thyristor T2 is turned on, so that again when it is fully discharged, okay, then again it will charge in a reverse direction, because here now plus and minus, okay, so it is discharged. Then once it is fully discharged, then the terminals has been changed, then again it will charge, okay, so with a the reverse polarities, which means the upper plate is positive and the lower plate is negative. So okay, then next what will happen? The capacitor C once again start to charge with the plus upper plate is positive and the lower plate is negative, so that the reverse biased applied, voltage applied across the thyristor T2, so that the thyristor T2 will also turn it off. So like this way, the whole process is repeating in this way. The whole process is repeating in this way. And one of the advantage of the class D commutation is the efficiency of the class D commutation is very high, because as we can see, the commutating energy is also transferred to the load, that we can see here. Okay, so the commutating energy, which means here the commutating element C. Okay, so these here the total load current will add up with this the actual load current flowing through this capacitor, and as well as the commutating current. So that's why the efficiency of this class D commutation is very high. Not very high, it is somewhat high when compared to the other commutation techniques. So this is the process of commutating, the class D commutation. So here just we are using this auxiliary thyristor to turn off the main thyristor, which means by turning on the auxiliary thyristor, so we are applying the reverse biased voltage across the thyristor, main thyristor T1, so that the thyristor T1 is turned off. Okay, so again here also, as you can see, same like in the previous commutation techniques, here the capacitor will play a major role. Like again what we are doing here, just we are charging and discharging the capacitor, which means we are providing the path to charge and discharge of the capacitor. So during this process only, here we are applying the commutation, which means just like we are applying the reverse biased voltage across the capacitor, so that the capacitor is going so that the reverse biased voltage across the thyristor, so that the thyristor is going to turn it off. This is about the class D commutation. And when coming to the waveforms in the class D commutation, okay, so here different parameters that we have considered here. Ig1 is the gate signal for the thyristor T1, that is the main thyristor, and Ig2 is the gate signal for the auxiliary thyristor, that is Tx, and here the It1 is the current flowing through the thyristor T1, and Vc is the voltage across the capacitor, and Ic is the current flowing through the capacitor, and I0 is the load current. As we assumed already, here the load current is constant. That's why here you can see the load current is constant, always constant. And initially we are turning on the thyristor T1 by giving the gate signal Ig1 to the thyristor T1. So the thyristor T1 is turned on. So when the thyristor T1 is turned on, then the voltage across the thyristor T1 is 0. Right? That's why here the voltage across the thyristor T1 is 0. Then whatever the current flowing through the thyristor, it is going to increase, because this is the current flowing through the thyristor T1. Then the voltage across the capacitor, initially as we have considered, the voltage, the capacitor is fully charged. So which means the voltage across the capacitor Vc is equal to Vdc. So that's why initially, okay, when it is turned on, the voltage across the capacitor Vc is equal to Vdc. But when the thyristor T1 is turned on, so we are providing the path to discharge the capacitor C. So that's why here the voltage across the capacitor is gradually decreasing. So at a particular point, the voltage across the capacitor will become 0, and after that the terminals has been changed. Then again it will charge in a reverse direction. So that's why during the charge again here the voltage across the capacitor is increasing up to certain point. So once it is increasing, once it is fully charged, which means again here Vc is equal to minus Vdc. Vc is equal to minus Vdc. Then the capacitor will, the maximum charging capability of the capacitor is Vdc only. So that's why here the capacitor is fully charged up to this extent. So after that, there is no path to discharge the capacitor. So that's why here the capacitor voltage is constant up to this point. Up to this point, the capacitor voltage is constant, which is minus Vdc. Then at this point, okay, so to turn off the thyristor, main thyristor T1, we are turning on the auxiliary thyristor Tx. That's why here you can see here the green color, the gate signal is given to the auxiliary thyristor Tx, then the thyristor Tx is turned on. So once the thyristor Tx is turned on, okay, then here a reverse biased voltage applied across the thyristor T1. So that's why here the reverse biased voltage applied across the thyristor T1. Okay, so because of the inductance effect, okay, okay, so I mean, because to turn off the thyristor we have to apply when the thyristor, when the reverse bias voltage applied across the thyristor, okay, still the thyristor will not turn it off immediately, okay, because the latching current, because the anode current will not be, is not reduced below the holding current. So that's why here some negative voltage that we are getting. Then after some instant of time, the thyristor T1 is turned off. Then again, when the thyristor auxiliary thyristor Tx is on, here as we can see here, this is the first case, okay, when the thyristor T1 is turned on, and the second case. So when we are turning on the auxiliary thyristor Tx, then reverse biased voltage applied across the T1, so that the T1 is will get into the off state and Tx is on. So which means we are providing the path for the capacitor to discharge in this way. So that's why here the capacitor voltage is gradually decreasing. Then again, the capacitor, once the capacitor is fully discharged, then the capacitor terminals will change. Then the capacitor will charge again with the polarities of the upper plate is positive and the lower plate is negative. This is our reference voltage. Then it will charge up to plus VDC. After plus VDC, it will again constant. This is how the capacitor, the output waveforms for the voltage across the capacitor, as well as the current across the capacitor, and the terminal voltage of the thyristor, as well as the current flowing through the thyristor. Right? Because here, as you can see here, during this time it is charging and discharging, so that's why here we are getting the capacitor current. But at a particular but once it is fully charged, okay, so up to here, once it is fully charged, so there is no path to discharge this capacitor. So that's why here the capacitor current is 0 until this part. So once we are turning on the auxiliary thyristor T on, then the capacitor, then we are providing the path through auxiliary thyristor Tx to discharge the capacitor. So that's why here it is discharging. So again here, that's why here the capacitor current is in the negative way. So again, once it is reached to here the capacitor current is discharged to 0. Then after that the terminals has been changed, and again it is charging fully with a upper plate is a positive and the lower plate is negative. Then once it is reached to plus VDC, again here there is no path to discharge the capacitor. So that's why here the capacitor current is 0 again. Okay, so this is how we can draw the waveforms. So based on the operation only, here we have drawn the waveforms. This is about the class D commutation. Then next one is the class E commutation. So this is very simple commutation. So here only the thing that we are using is the pulse transformer. By using this pulse transformer, we are going to apply the the commutation. So here we are connecting the thyristor to the primary side, and the secondary of the pulse we are connecting the thyristor, okay, in series with the secondary of the pulse transformer. Okay, so in addition to the the thyristor, so here we are also included the capacitor and the resistor. But here unlike in the previous commutation techniques from class A to class D, okay, so here the major components are not the capacitor. Here the major component is the pulse transformer. So initially, again the process initially by giving the gate signal to the thyristor T1, okay, so we are turning on the thyristor T1. So during this time, the load current is flowing through the secondary of the pulse transformer and the load. Okay, so this is the secondary, this is the primary, and this is the secondary of the pulse transformer. Then when a pulse is given to the primary of the pulse transformer, then the voltage across the secondary of the pulse transformer will get reversed, that is minus VDC. So that minus VDC, which means the reverse biased voltage will apply across the thyristor T1, which means here the anode is negative with respect to the cathode, then the thyristor will get to the turn off. The thyristor will get into the turn off. So here again, of course, here we are connecting the capacitor across the what is that thyristor. I mean, the series combination of the thyristor and the secondary of the pulse transformer. The secondary of the pulse transformer. Okay, but anyway, here the voltage drop across this thyristor is very low because the frequency of the pulse transformer is very high. Usually, we consider the frequency of the pulse transformer is very high. So that's why here the voltage drop across the capacitor is very low. So that's why here we neglect the voltage drop across the capacitor, and even which is the around, I mean, the maximum it can be 1 volt only. So that's why we won't consider the voltage drop across the capacitor. So here the very simple commutation technique here it is, but here we need to use the pulse transformer. By using the pulse transformer only we can apply the commutation. Then the other commutation technique is the class F commutation, which is the natural commutation. Because as we know, there are mainly two different types of commutation based on the input supply. So if we consider a thyristor, here this is a thyristor. Okay, so if you are apply a DC, this is the DC for this across the thyristor, then here we use the forced commutation. The forced commutation technique, and here we are applying the AC, then here we use the natural commutation. Why? Because here in all the commutation techniques from A to E, okay, so how we have, how we turn it off the thyristor by applying the reverse biased voltage across the thyristor. Because as we know, if you want to turn off the thyristor, it must satisfy two conditions. One is you must apply the reverse biased voltage, and the second one is by applying the reverse biased voltage, you must reduce the anode current below the holding current. Anode current below the holding current. So you must satisfy these two conditions, then only the thyristor will get into the turn off. Right? So when you consider the supply is a DC, okay, which means like this. So here, which means it is always the positive supply, which means it is always the positive, the forward biased voltage across the thyristor. So that's why, to apply the reverse biased voltage or to get the reverse biased voltage across the thyristor, so we are using the different types of commutation techniques, that is class A, class B, class C, class D, and class E. But unlike in the forced commutation, in the natural commutation, as you can see, when input is AC supply, here the AC supply having the two cycles, especially, that is this is the positive cycle and this is the negative cycle, right? So here if you give the AC supply to a particular thyristor, so during the positive cycle, here the anode is positive with respect to the cathode. So which means the forward biased applied. Again, to turn on the thyristor, what we have to do? We have to apply the forward biased voltage, and as well as we must give the gate signal, right? So here, if you, during the positive cycle, here the forward biased voltage applied across the thyristor T1, which means the anode is positive with respect to the cathode, and when you are giving the gate signal to the thyristor, then the thyristor will turn on so that the load current will flow in this way. The load current will flow in this way. Okay, so that's why here you will get the whatever the supply current that you are applied, the same amount of the current that you will get across the load. So that's why here it is following the same as like the supply waveform. And after pi, okay, so the negative cycle is applying across the thyristor. Okay, so which means here in this case the anode is negative with respect to the cathode. The anode is negative with respect to the cathode, then the thyristor will get into the turn off. So which means turn off means there is no current will flow from source to the load, so that the load voltage is 0 here. Then again after 2 pi, then again the positive cycle will apply across the thyristor T1 plus and minus. Then again the thyristor will get turn on by giving the gate signal. Then again the load current will flow through the load. Then again you will get the output voltage. Similarly, after 3 pi, then again the negative supply, the negative cycle. So because of the negative cycle, again the reverse biased voltage applied across the thyristor T1, then the thyristor T1 will turn off, then there is no load current. So that's why here again it is 0. This is how the natural commutation is happening. Why it is a natural? Because of the nature of the AC waveform. So without doing anything or without connecting any extra commuting elements or commutation circuit, so the thyristor is the thyristor is turning off. That's why it is a natural commutation, because of the nature of the AC voltage waveform. So during the negative cycle, automatically it is applying the reverse biased voltage across the thyristor. So that's why it is turning off. Right. So this is how the natural commutation will work. Then when coming to the voltage across the thyristor, anyway, up to pi here, the forward biased voltage applied, and we are giving the gate signal. So that's why the thyristor T is turn on. So during the turn on, the voltage across the thyristor is 0. And during the turn off, okay, so the voltage across the thyristor is whatever the voltage, the supply voltage that we are applied, the same amount we will get across the thyristor, that is minus Vm. The peak is. So similarly, again after 2 pi the thyristor will turn on, so 0 voltage, and again after 3 pi the thyristor will turn off, then you will get the same supply voltage whatever you are applying. This is how the commutation process is taking place in case of natural commutation. So what are the different, which means what are the different converters that will having the input as the AC supply? That is, one is AC to DC converters, another one is AC to AC converters. So AC to DC converters are rectifiers, and again AC to DC converters, there are two different types of converters are there. One is AC voltage controller, and another one is cyclo converter. So in these three different types of converters, we use the natural commutation. So, and the remaining converters are, those who are having the DC supply as an input, DC to AC and DC to DC. So DC to AC are inverters, and DC to DC are choppers. So in case of inverters and choppers, we use the forced commutation techniques, like from class A to E. This is about the different commutation techniques of an SCR. Then in the previous class, we have also discussed the gate characteristics of an SCR. Okay, So based on the gate characteristics of an SCR, so today, in this class, we are going to discuss some numerical problems. And before going to discuss about the gate characteristics of an SCR, the numerical problems on gate characteristics of an SCR. So let me discuss the another topic, which is the SCR protection techniques. SCR protection techniques. So which means from which parameters or from which elements we need to protect the thyristors. One is here I have listed out. One is di by dt protection, another one is the dv by dt protection, then over voltage and over current, which means we must protect the thyristor from di by dt, and we must protect the thyristor from dv by dt, and also we must protect the thyristor from over voltage and over current. So to protect the thyristor from di by dt, so what we have to do, and to protect the thyristor from dv by dt, and similarly from over voltage and over current, what we are going to do, that we will discuss here. So before that, we should know what is di by dt and dv by dt, so that we can know, how we can protect the thyristors from di by dt as well as the dv by dt. So first, we will discuss about the di by dt protection. So then di by dt is nothing but the rate of change of current in the device. The rate of change of current in the device. So when SCR is forward biased and gate pulse is applied, then the anode current will flow through the thyristor, right? So because here when an SCR, to turn on the thyristor, again I am just repeating, to turn on the thyristor it must satisfy two conditions. One is we must apply the forward biased voltage across the thyristor, as well as we must give the gate current. Okay, so why we are applying the forward biased and the gate current? To increase the anode current above the latching current, then only the thyristor will turn on, right? So which means we are increasing the anode current by applying the forward biased voltage across the thyristor, and by applying the gate signal to the thyristor. Then these anode current require some time to spread inside the device. Okay, so which means the rate of increasing the anode current. Okay, it means change means it may be increase or it may be decrease. So because for the turn on, we are going to increase the anode current above the latching current. So that's why here we can consider, because we are considering this di by dt rating during the turn on process. So that's why we can consider as a increasing here the di by dt, which means the current is increasing. So the rate of change of increase the current is the di by dt. So if the anode current required some time to spread inside the device, okay, so if di by dt is greater than the spread velocity of charge, okay, which means if the di by dt is greater, which means the rate of change of increasing the current is greater than the spread velocity of the charge, then it creates some hot spots, so that the thyristor may get damaged. So to prevent or to control the rate of change of current, or the rate of increase of the current, that is di by dt. So here we are connecting one inductor in series with the SCR, because as we know, the basic function of the inductor is it will oppose the sudden change in the current. It will oppose the sudden change in the current. So that's why here we are inserting one inductor in series with the thyristor to protect from di by dt. To protect from di by dt, which means to protect from rate of change of current. Right? Then how to choose the inductance value to include in series with the thyristor? So that is, as we know, the general equation, the voltage across the the inductor, which is equal to L into di by dt. So from this we can get L is equal to Vs by di by dt. So which means the L value must be greater than Vs by di by dt. So in this way we have to choose the inductance value which we are going to connect in series with the thyristor. This is about the di by dt protection, which means we are protecting the thyristor from di by dt, or we are protecting the thyristor sudden change in the current or rate of change of the current. Then the next one is dv by dt protection. So the dv by dt protection, I mean, again, the dv by dt is nothing but the rate of change of voltage in the device. The rate of change of voltage in the device. So, which means if high value of dv by dt is applied across the thyristor, so it may cause for false turn on and the false turn off. False turn on and the false turn off, because which means it may turn on before, I mean, false turn on means when, I mean, even though at that particular point we don't require to turn on the thyristor, but it will turn on. So that it means the false turn on and false turn off. So to avoid the false turn on and false turn off caused by the high value of the dv by dt, so here we are using the snubber circuit. The snubber circuit is nothing but if you connect, I mean, the series connection of the R and C elements. This is called the snubber circuit. The series RC elements are called the snubber circuit. So by using the snubber circuit, we can protect the high, what is that, the rate of change of the voltage. Because as you can see, I mean, the current will flow in series and the voltage will get across the capacitor. So that's why here, to protect the thyristor from di by dt rating, so there we have connected the inductor in series, and here we are connecting these capacitor in parallel, especially here the capacitor. So the capacitor is connected to bypass the high dv by dt voltage. And here the resistor is connected to decrease the discharge current of the capacitor through SCR. To decrease the discharge current of the capacitor through SCR. So for that reason, here we are using the resistor. So this is how we can protect the thyristor from the dv by dt rating. Then the over voltage and the over current protection. So to protect the SCR from the over voltages, then we just connect a fuse. Okay. Then the SCR protected against the extra extra over voltage through the fuse arrangement. Then for the over current protection, so we will connect a resistor across the SCR, okay, to prevent the over current protection. So this is how we can avoid the damage or the false function of the SCR due to di by dt and dv by dt, and as well as over current and over voltage. This is about the protection of the SCR. The next we are going to discuss one numerical problem on the gate characteristics of an SCR. Okay, so here let me read the problem. Here, the make use of gate triggering technique to find gate source resistance of an SCR with gate cathode characteristics has a straight line slope of 130 and trigger source voltage of 15 volts and allowable gate power dissipation of 0.5 watts. So first, for any kind of problem, first we have to understand what is the given data, and from the given data what we have to find. So here what we have to find, the gate source resistance, that we need to find. So as we know, the general equation, that is Vs, okay, that is the source voltage applied across the gate and cathode. Vs is equal to Vg, which means the voltage across the gate and cathode, plus Ig into we can Rs or let me consider Rs. So from this equation we have to find what is the value of Rs. And here the given data is, they have given the power Pg, the gate power Pg, which is equal to Vg into Ig, which is equal to 0.5 watts. And again what they have given, the straight line slope, the characteristics. Actually here the characteristics are, here you can see the characteristics of the Here you can see the gate characteristics of an SCR. So here the slope of the gate characteristics, which means here the actual gate characteristics are S1 and S2 are AD, the line AD which represents the actual gate characteristics. So here AD is equal to here VG by IG, because here the slope AD is equal to, actually AD is equal to, what is that, OA by OD. Here OA represents, this OA represents VG, and this OA represents, OD represents IG. Okay, and from this data we have to find the value of the R. Okay, so for that let me explain here. I have given step by step explanation. So as I mentioned here, they have given the power dissipation, I mean the gate power dissipation, which is the PG. PG is equal to VG into IG, so that is 0.5 watts. And again another what is that thing that they have given is VG by IG is equal to 130, which is the slope or the characteristics of an gate characteristics, that is AD is equal to what is that, to OA by OD. Okay, so here OA is VG and OD is IG. So from these two equations, by solving these two, because here we are having the two equations 1 and 2, and by solving, and we are having the two unknown parameters VG and IG. So by solving these two equations, you can get the value of VG as well as the value of the IG. So here for that, what we have done here, from this equation VG is equal to 130 into IG. So this equation, the VG value, we are going to substitute in this equation 1. Then here in the place of VG, if you substitute 130 into IG, so already here 130 into IG, already IG is there here into IG, which is equal to 0.5. So that 130 IG square equal to 0.5. Then from this you can find easily IG, okay, which is equal to 0.5 by 130 square root, right? So then here, as you can see, from this equation you can find IG, that IG is equal to 62 milliamperes. Then if you substitute these IG value in this equation, then you will get, because VG is equal to 130 into IG, so 130 into IG is here 62 into 10 to the power of minus 3, because milliamperes. Okay, so then you will get the voltage VG, which is 8.06 volts. So you are having VG and IG, then you know the standard equation Vs. Okay, because the trigger source voltage also they have given. Okay, the trigger source voltage. So Vs is equal to Vg plus Ig into R. So from this, in this equation, you know what is Vs. Vs is equal to 15 volts and Vg is equal to 8.06 plus Ig is equal to 62 into 10 to the power of minus 3 into R. So in this, from this equation, from this value, I mean by solving this equation, you can find the value of the R. So that's how here, of course, sometimes maybe they may consider Vs or Es. So Es is equal to Ig into Rs plus Vg. So you know what is Es, which is 15, and here Ig is 62 into 10 to the power of minus 3, and Vg is equal to 8.06. Then by solving this equation, then you will get the value of the Rs, which is equal to 111.94 ohms. This is how we have to find the gate source resistance. So here, if you want to solve this problem, we must aware about the gate characteristics. Then only we can solve, because from these gate characteristics only, I mean, we got the relation, that is Vg by Ig is equal to 130. Okay, without this relation, we cannot solve, or we cannot find Vg and Ig values. Okay, so that's why here it is very important. So in the next class, we will discuss the further topics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.